Welcome to our next video in our series on condensed matter theory. Today I want to talk a little bit about the theoretical methods or toolkits that we have, just giving you an overview for the different types of things that we will discuss during this lecture in condensed matter theory. As we saw in the previous lectures, we have a very good understanding of the microscopic interaction between our constituents of a solid, but the more complexity of our system still gives rise to very interesting behavior in our systems and a very rich physics. It's actually this complexity and the emergent behavior that makes our world so rich. So that's a good thing. But of course we have to find ways to deal with it. And for this we have several different options that we can make. And let me just give you an overview of the different types of things that we can do. And the first thing that we can do is make approximations. If our Hamiltonian is too difficult to solve, we're going to simplify it and see if we still get reasonable results. And one approximation that has been very successful is to replace the Coulomb interaction, E square over Ri minus Rj, by a potential. And a potential we only have to sum over the coordinates of one electron, and for the Coulomb interaction we have to sum over all pairs of electrons. And this change from a sum over all pairs to just a sum over one electron helps to remove entanglement between your electrons, because for many electrons moving in a potential, you can always find a representation of your wave function that is given by a single Slater determinant. Then on that basis there is no entanglement, and that hugely simplifies the problem. This is known as mean field theory. And one of the better known mean field methods are the Hartree-Fock approximation, which we will encounter later in this lecture, and density functional theory. Now, many people would say density functional theory is not a mean field approximation because density functional theory is formally exact, which is true, but all practical implementations that we have of density functional theory are mean field approximations, just not the Hartree-Fock approximation. So that's why I basically put it here. If you give me a density functional theory that is not a mean field, then we can discuss further. But these successful ones are mean field approximations. It is still one of the most successful approximations that we have. And it is this method that works for about 1/3 of the materials, so which you can use to describe your semiconductor electronics or titanium or aluminum. But that's also going to fail on magnetism or correlated systems, transition metals, superconductivity, and many more. So it works for about 1/3 of your materials. Not bad, not something to be fully satisfied with. Then what people tried is to start from your mean field theory and do perturbation theory. Well, it is numerically heavy. But that is not the biggest problem with perturbation theory. Be clear, there are cases where if you have a small perturbation, it's absolutely the way to go. But in condensed matter systems, the Coulomb interaction is not a small perturbation. We've seen in the hydrogen atom, the Coulomb energy is of the same energy scale as your kinetic energy. So you're approximating here actually a large part of your interaction. And why perturbation theory might fail and not even say being not accurate or you have to go to very high orders, but giving you completely wrong results, we can see when we realize that perturbation theory is basically a Taylor series expansion, where you expand in orders of the Hamiltonian. And when that is small, or the perturbing Hamiltonian, if that is small, it's fine. If that is big, you have to be careful. So let's have a look at how perturbation theory can fail by doing the analog why Taylor series might fail. So what we see here are two functions, f of x in blue and g of x in orange. They're smooth functions, infinitely differentiable. On the real axis everything is very fine, they nicely converge, they go to 0 for large x, all well behaved. We can now make a Taylor series expansion in the point x is 0. If we do this, then the first order is just a linear approximation, which beautifully works. It's a constant for the orange line and a straight line with a slope for the blue line, all well. We can go to higher orders in our perturbation theory, and for the 10th order you see that in an interval from 0 to 1 you have very good agreement between the Taylor series, so a polynomial of 10th order, and the original functions. Of course, for higher values of x, things start to deviate, but we'll just make the order of the series higher and things should get better and better. If we do that, here a 100th order polynomial expansion in a Taylor series, then we see for the blue line all works fine. They're basically completely on top. The orange line is extremely well for x smaller than some 1.3 or so, 1.2, 1.4, but then the deviation already kicks in very steep. We can perfectly see that there is, for larger x, it doesn't work. It's not even close, it's not even an approximation, it's just completely different. So why is this? If we look at g of x, then its denominator can become 0, which means that g of x diverges. Well, not on the real axis. For the denominator to be 0, x plus 1 has to be equal to minus 1. So if we look in the complex plane and look at the poles of g of x, then we see at minus 1 plus I or minus 1 minus I, g of x diverges. That gives you a convergence radius of square root of 2, and that means that inside your range of convergence a Taylor series works, and outside your range of convergence a Taylor series doesn't work. The same is true for perturbation theory. When your perturbing Hamiltonian is small, you have a convergent series. When it is large, you have a divergent series. It's although not always so easy as in this example to see if you converge or diverge. So that's perturbation theory. Only works if your perturbing Hamiltonian is small, and in condensed matter theory, Coulomb interaction is not small. There are actually nowadays numerical methods where you can really test this, and there are many examples in the recent literature where people show that these kind of perturbative approximations do not work and lead to incorrect results in condensed matter systems. So other methods, and one that Heidelberg is known for is renormalization group theory. In renormalization group theory, people try to derive a new, effective, low-energy Hamiltonian that acts on your quasi-particles starting from the full Hamiltonian. This is in an early stage of development. We will not really discuss renormalization group theory, although several of the approximations that we do, or several of the models that we solve, for example, when we calculate surface states, are completely formulated in the language of renormalization group theory. And when you follow such a lecture later on, or have followed it before, then you will recognize some of the steps that we take, and you will be able to reformulate this in the renormalization language very easily. That's also one of the reasons that we will go to Green's functions and second quantization in our lecture, just to make that connection and make it easier to make that connection. So it's definitely worth the effort of notation that we have to get acquainted to. So the last option that we can use is just to make effective models. We can propose new effective Hamiltonians that we then can solve and describe the material properties at hand. And for example, the spontaneous symmetry breaking that we have in crystals, we will just propose an Hamiltonian that has this symmetry breaking, and then of course the solutions will be symmetry broken. So we never really explain why nature breaks these symmetries spontaneous, but we just put that in the Hamiltonian as an ingredient in an effective model. And with that we can describe our systems and even do phase transitions where you change between different symmetry broken phases. And these are then just your effective interactions between the quasi-particles that we see, which is based on experiment. But then again, also our microscopic interactions and Hamiltonians, the Schrödinger equation, is something based on experiment. We've seen certain things happen in experiment, Planck, and therefore Planck observed the black body radiation, and therefore we propose these kind of theories and models to describe those. Very good. The next lectures will be a bit on the mathematical notation, second quantization that we use in quantum mechanics. And before I introduce second quantization, I want to talk about why it is important to use second quantization. It's not just there because we like Heideggers instead of wave functions, but it solves a problem that you have when you want to write down wave functions. And that problem I can introduce nicely by starting with the Pauli principle and why that results in the need to antisymmetrize your wave functions. So we'll present briefly the Pauli principle and how that leads to the problem that we can't write down our wave functions, or not on a finite amount of paper, and we solve that with using second quantization. Stay healthy, we see each other next time.